Welcome to the ultimate journey through real-time computer vision. I am Shadi Syed, and in this course, we will completely demystify the you only look once, or YOLO architecture. Over the next series of lessons, we will explore how AI learned to perceive the world at the speed of life, from its disruptive single-pass beginnings to the highly advanced, edge-optimized powerhouses of today.
Imagine you walk into a room full of toys. In less than 1 second, your brain already knows there's a teddy bear on the shelf, a red ball on the floor, and a toy car under the table. You didn't look at each object one at a time, your brain saw everything at once. That, my friend, is what YOLO tries to teach a computer to do.
Object detection is like being a detective with a magnifying glass, except you don't just find clues, you also draw a box around each clue and label what it is. A computer doing object detection must answer 2 questions. Where is the object and what is the object?
Before we teach a computer to detect objects, we need to understand how a computer even sees an image. To you, a photo of a dog is a dog. To a computer, that same photo is a giant spreadsheet of numbers, thousands of tiny colored squares called pixels. Each pixel has 3 numbers, 1 for red, 1 for green, and 1 for blue.
A computer isn't born knowing what a dog looks like. You have to teach it by showing it thousands of labeled examples. This is called supervised learning. Show the computer 10,000 photos labeled dog and 10,000 labeled cat, and it gradually learns the patterns that distinguish one from the other, the shapes of ears, the texture of fur, the length of tails.
Your brain has about 86 billion tiny workers called neurons. Each neuron receives signals, does a tiny calculation, and passes its answer to the next neuron. A neural network inside a computer works the same way. It's a chain of mathematical neurons. Simple inputs go in, and smart outputs come out.
Think of the connections between neurons as volume knobs on a mixing board. Each knob controls how loud one signal is compared to another. A large weight means that input is very important. A small weight means it barely matters. A negative weight means it actively suppresses the signal. These weights are the actual knowledge the network learns, millions of carefully tuned numbers.
When the network makes a wrong prediction, it goes back and turns the knobs a tiny bit. This is called backpropagation. It's like a student who gets a test back with a grade. The student looks at each wrong answer, traces back to which study habit caused the mistake, and adjusts. Over thousands of tests, the student masters the subject. The network does the exact same thing with calculus.
Imagine you have a rubber stamp that's 3 by 3 squares. You press this stamp onto your photo, slide it across every position, and at each stop you multiply the stamp's numbers by the photo's numbers and add them up. That's a convolution. Different stamps, called filters or kernels, detect different features, edges, corners, textures, and eventually whole objects.
When the filter slides across the image, how far it moves each step is called the stride. A stride of 1 means it moves 1 pixel at a time, very thorough, but the output stays large. A stride of 2 means it skips every other position, faster, and the output shrinks to half the size. Padding adds extra blank pixels around the edges so the filter can reach the corners without shrinking the image.
After convolutions, we sometimes shrink the feature map using pooling. Max pooling looks at a small window, say 2 by 2, and keeps only the largest value. It's like reading a long book and writing down only the most important sentence from each chapter. You lose the filler, but you keep the key ideas. This makes the network faster and more focused.
After each neuron does its math, it passes the result through an activation function, a rule that decides how much signal to let through. ReLU says, if positive, keep it; if negative, make it 0. Leaky ReLU lets a tiny bit of negativity through. These functions add nonlinearity. Without them, stacking layers would be pointless because a chain of linear operations is just one big linear operation.
Now imagine you stack hundreds of these filters in a pipeline. The first filters find simple things like edges. The next filters combine edges into shapes like circles and rectangles. Deeper filters combine shapes into parts, eyes, wheels, wings. The deepest filters recognize whole objects, faces, cars, birds. This pipeline is a convolutional neural network, or CNN, the engine inside YOLO.
Training a CNN from scratch requires millions of images and days of computing. But there's a shortcut called transfer learning. First, train the network on a massive general dataset like ImageNet, 1 million photos of 1,000 categories. The network learns universal features, edges, textures, shapes. Then, swap out the last layers and fine-tune on your specific task. YOLO v1 pre-trained its first 20 layers on ImageNet before learning detection.
Let's meet three siblings in computer vision. Classification says what is in the image, just a label. Detection says what and where, labels plus boxes. Segmentation says what, WHERE, and the exact shape, painting every pixel that belongs to an object. YOLO started as a detector but now handles all three and pose estimation too.
Before YOLO, the popular way to detect objects was a two-step dance. Step 1. Scan the image and propose thousands of regions that might contain an object. Step 2. Classify each region. It's like searching for your keys by opening every single drawer in the house one by one. Accurate? Yes. Fast? Absolutely not.
The two-stage detectors like faster RCNN processed about 5 frames per second. That might sound fast, but a self-driving car needs at least 30 frames per second. A surveillance camera streams 25 frames per second. A drone dodging obstacles needs even more. At 5 FPS, 5 out of every 6 frames go unanalyzed. The world desperately needed a faster approach.
In 2015, a brilliant and unconventional researcher named Joseph Redmon asked a radical question. What if we skip the region proposals entirely? What if we just look at the entire image once and predict all the objects in a single pass? He called his invention YOLO, you only look once, and it changed computer vision forever.
The key insight is deceptively simple. Instead of first finding regions and then classifying them in 2 steps, YOLO does everything in a single forward pass through one neural network. The network takes the entire image and directly outputs all bounding boxes and class probabilities at once. It's like reading a whole page at a glance instead of one word at a time.
Here's YOLO's first trick. Take your image and draw a grid on it like a chessboard. YOLO V1 used a 7x7 grid, creating 49 cells. Each cell is responsible for detecting objects whose center falls inside that cell. Think of it like dividing a city into neighborhoods, and each neighborhood watch team reports crimes on their block.
Each grid cell in YOLO V1 predicts 2 bounding boxes. For each box, 5 numbers: the X and Y coordinates of the center relative to the cell, the width and height relative to the whole image, and a confidence score. The cell also predicts 20 class probabilities shared across both boxes. That's 2 times 5 plus 20 equals 30 numbers per cell. Multiply by 49 cells and you get 1,470 predictions from a single image.
The confidence score is not just yes or no. It encodes 2 things multiplied together: the probability that any object exists in the box, and the intersection over union between the predicted box and the ground truth. Empty box means confidence 0. Perfect box wrapping an object means confidence near 1. This elegant formulation rewards both finding objects and localizing them precisely.
Imagine throwing a blanket over a sleeping cat. A perfect throw covers only the cat IOU of 1. If the blanket also covers half the couch, IOU drops to around 0.5. Miss the cat entirely and IOU is 0. IOU, intersection over union, is the universal measuring stick for how well a predicted box matches the real object's box. It's used everywhere: in training, in NMS, and in evaluation.
After YOLO makes predictions, multiple cells might detect the same object, creating overlapping boxes. Imagine 10 people pointing at the same bird shouting, "I see it." We only need one report. NMS keeps only the most confident box for each object and removes overlapping duplicates. It sorts boxes by confidence, picks the best, calculates IView with all others, removes anything above the IView threshold and repeats.
The brain of YOLO V1 is 24 convolutional layers followed by 2 fully connected layers. Input: 448 by 448 pixels. The conv layers extract features from simple edges to complex objects. The fully connected layers produce the final 7 by 7 by 30 tensor. The first 20 conv layers were pre-trained on ImageNet. The whole thing runs at 45 frames per second, 90 times faster than fast RCNN.
How does YOLO learn? Through its loss function, a recipe measuring how wrong predictions are. 3 ingredients: localization loss for box coordinates, confidence loss for objectness, and classification loss for class labels. The loss uses sum of squared errors for everything. 2 special weights. Lambda coord equals 5 makes box accuracy matter more, and lambda nubage equals 0.5 reduces the penalty for empty cells, since most cells contain no objects.
YOLO V1 was revolutionary but not perfect. It struggled with small objects because the 7x7 grid was too coarse. Clusters of small objects overwhelmed cells limited to 2 boxes. Unusual aspect ratios like long trains were poorly predicted, and localization accuracy lagged behind 2-stage detectors. But these limitations were a roadmap, not a dead end. Each became a feature in the next generation.
2017 brought YOLO v2, also called YOLO 9000 because it could detect 9,000 categories. The biggest change was anchor boxes, of predefined box shapes that give the network a head start. It also added batch normalization to every layer, removed the fully connected layers, increased resolution to 416 by 416, and introduced multi-scale training. The result, 78.6% MAP at 67 FPS.
Think of anchor boxes like cookie cutters. You don't sculpt each cookie from scratch. You press a pre-shaped cutter into the dough and adjust. YOLO v2 analyzed the training data with k-means clustering and found 5 common shapes objects tend to come in. Tall, thin for people, wide, flat for cars, square for faces, and so on. The network then only needs to learn small adjustments, stretch a bit here, nudge a bit there.
Imagine a classroom where one student whispers and another screams. The teacher can't process both. Batch normalization gives every student the same microphone volume. Technically, it normalizes each layer's inputs to have zero mean and unit variance, then lets the network learn the optimal scale and shift. Adding BN to every layer in YOLO v2 boosted MAP by 2% and made training faster and more stable.
YOLO v2 introduced DarkNet 19, a custom 19-layer backbone. Think of the backbone as the spine, the core feature extractor. YOLO v3 upgraded to DarkNet 53 with 53 layers and residual connections from RaisNet. These skip connections let gradients flow directly through shortcut paths, solving the vanishing gradient problem and enabling much deeper networks without losing training signal.
YOLO v3 in 2018 was all about detecting objects at 3 different scales. It's like having 3 security cameras, wide angle for big objects, standard for medium, and zoom for small. The network predicts at 13x13, 26x26, and 52x52 grids using a feature pyramid network. With 3 anchor boxes per scale, that's 10,647 prediction boxes per image, vastly more than YOLO v1's 98.
FPN is like building a layer cake and tasting every layer. Early CNN layers have fine spatial detail but basic features. Deep layers have rich semantics but coarse detail. FPN combines both. It takes deep features and upsamples them back to earlier resolutions, then concatenates with earlier feature maps. The result? Every scale gets both fine detail and rich understanding.
Modern YOLO has 3 sections: backbone, neck, and head. The backbone extracts features. The head makes predictions. The neck sits between them, fusing features from different scales. Think of it as a river delta. Water flows downstream from mountains, deep features. Then tributaries feed back upstream, fine details, creating a rich interconnected network that feeds 3 fertile detection planes.
In 2020 brought YOLO v4 from Alexei Bachkovsky's team. Not one big innovation, but a masterful combination of every cutting-edge trick. CSP DarkNet 53 backbone, SBP block, PONet neck, mosaic augmentation, CIOU loss misactivation. The team categorized tricks into bag of freebies, free improvements during training, and bag of specials, slight inference cost for big accuracy gains.
Mosaic stitches 4 random training images into one collage. Objects appear at unusual scales and contexts in every training step. It's like studying 4 textbook pages simultaneously, 4 times the diversity per iteration. This also reduces the need for large batch sizes because the 4 subimages provide sufficient statistical variety for batch normalization.
YOLO v5 from Glenn Jotcher at Ultralytics in 2020 was controversial, no research paper, just a beautifully engineered open-source PyTorch codebase. But it became the most popular YOLO ever because anyone could use it. 5 model sizes from nano to X-large, auto-anchor learning, 1 command training, export to 11 formats. YOLO v5 democratized object detection.
YOLO v6 from Meituan in 2022 was built for factories, not labs. Its key trick was reparameterization, using a complex multi-branch architecture during training for richer gradients, then mathematically fusing all branches into a single fast convolution for deployment. Think of it as studying with detailed mind maps, then condensing everything into a 1-page cheat sheet for the exam.
YOLO v7 from the Wang Qin team in 2022 was about scaling intelligently. Its Elon module optimized feature aggregation using group convolutions with channel shuffle. Its compound scaling strategy adjusted depth, width, and resolution simultaneously, like a tailor altering a suit's length, width, and fabric quality together rather than one at a time.
YOLO v8 from Ultralytics in 2023 unified 5 tasks into one framework: detection, segmentation, classification, pose estimation, and tracking. It made 3 architectural leaps: anchor-free detection, no more cookie cutters, a decoupled head, separate experts for what and where, and task-aligned assignment for smarter training. It became the most versatile YOLO ever.
Remember the cookie cutters. Anchor-free detection throws them away entirely. Instead of adjusting templates, the network directly predicts distances from each point to the 4 edges of the box. Point at an object's center and say, top edge is 30 pixels up, bottom is 50 down, left is 20 left, right is 40 right. Simpler, fewer hyperparameters, no k-means clustering needed.
YOLO v9 in 2024 tackled a deep problem: information loss in deep networks. As data flows through 50+ layers, information degrades like a game of telephone. PGI, programmable gradient information, adds an auxiliary branch that preserves clean information and feeds reliable gradients back during training. GELAN, generalized ELAN, provides flexible, efficient feature aggregation. Together, they achieved state-of-the-art with 25% fewer parameters.
YOLO v10 in 2024 from Tsinghua University eliminated NMS entirely. The trick: dual assignment heads. During training, a one-to-many head matches each object to multiple predictions for rich gradient signal. During inference, a one-to-one head matches each object to exactly one prediction, clean output, no duplicates, no post-processing. The NMS grinder is gone. End-to-end detection is here.
YOLO 11 from Ultralytics in late 2024 introduced C3K2 blocks, efficient feature extraction with smaller kernels, and the C2PSA module combining cross-stage partial connections with spatial attention. Attention lets the network focus on important parts of an image, like how your eyes lock onto a face in a crowd, rather than wasting effort on the blank sky above.
For over a decade, every YOLO backbone relied on stacks of convolutions. YOLO v12 breaks that tradition by placing self-attention at the very center of the detector, while keeping real-time speed. Think of it this way. Convolutions are like reading a book one sentence at a time, but attention lets you glance at the whole page at once and focus on the important paragraphs.
Standard self-attention compares every pixel to every other pixel. That is N2 complexity and far too slow for real-time use. Area attention solves this cleverly. It slices the feature map into a small number of equal regions, say 4 horizontal strips, and performs full attention only within each strip. Imagine reading a newspaper. You do not compare every word on the page to every other word. You read column by column. Each column is still large enough to capture context, but the total work shrinks dramatically.
Stacking many attention blocks can make training unstable, gradients vanish or explode. YOLO v12 introduces Elan, an upgraded version of the Elan module from YOLO v7. Think of it like adding guardrails to a tall staircase. Each floor has a short side path that lets the signal bypass the main stairway if it gets weak. Elan adds a block-level residual shortcut with a learnable scaling factor, so the network can smoothly decide how much of the new information to blend in.
Two more tricks make YOLO v12 practical. First, flash attention rewrites the attention kernel to minimize GPU memory reads and writes, like reorganizing your desk so everything you need is within arm's reach instead of across the room. Second, since YOLO v12 removes explicit positional encoding, it adds a 7x7 depthwise separable convolution inside each block, a position perceiver, that implicitly tells the network where each feature sits.
Let us see the numbers. YOLO v12 Nano gets 40.6 MAP on Coco at 1.64 ms on a T4 GPU. That is 2.1% better than YOLO v10 N and 1.2% better than YOLO 11N at the large end. YOLO v12X reaches 55.2 MAP. The trade-off: YOLO v12 uses flash attention and can be memory hungry, and it is slower on CPUs than pure CNN models. For GPU-rich environments it shines. For edge CPUs, YOLO 11 or YOLO 26 may be better.
If attention captures pairwise relationships, pixel A relates to pixel B. Hypergraphs capture group relationships. Pixels A, B, and C are all part of the same object simultaneously. YOLO v13, released in June 2025, introduces hypergraph-based adaptive correlation enhancement. Think of a group chat versus a one-on-one call. A hyperedge connects multiple nodes at once, capturing higher-order patterns that pairwise attention misses.
YOLO v13 does not stop at the backbone. It introduces full pipeline aggregation and distribution, or full PAD. Instead of fusing features only in the neck, full PAD distributes hypergraph-enhanced features to every stage of the network: backbone, neck, and head. It is like a hospital where a specialist's notes are shared not just with the surgeon but with every department: triage, lab, and pharmacy. Everyone benefits.
In January 2026, Ultralytics released YOLO 26, purpose-built for edge and low-power devices. If YOLO v12 was the attention-powered sports car for GPU racetracks, YOLO 26 is the fuel-efficient hybrid engineered for city driving. Its Nano model runs 43% faster on CPU than YOLO 11N, and it removes the need for non-maximum suppression entirely, Predictions come out clean in one shot.
Distribution focal loss was introduced in G-focal to model bounding box edges as probability distributions rather than single numbers. It improved accuracy, but added a 16-bin softmax per coordinate, complicating export to lightweight runtimes. YOLO 26 removes DFL and instead relies on improved regression targets and prog loss. Imagine a chef who used to plate food with 16 garnishes per dish, beautiful but slow. Now the chef uses 4 perfectly chosen garnishes that taste just as good, and the kitchen runs twice as fast.
YOLO 26 introduces MuSGD, a hybrid optimizer combining classic SGD momentum with the Muon optimizer developed for large language models. Muon was used in training Moonshot AI's Kimi K2 model and showed faster convergence in huge parameter spaces. MuSGD adapts this for vision. It uses Muon's adaptive gradient scaling for convolutional layers and standard SGD for batch norm and bias parameters. Think of it like a bilingual coach who speaks language model to the big layers and classic vision to the small ones.
The numbers tell the story. YOLO 26N, 40.9 MAP, 38.9 ms CPU, 1.7 ms T4, 2.4 M params. YOLO 26X, 57.5 MAP, 526 ms CPU, 11.8 ms T4, 55.7 M params. Compared to YOLO V12, YOLO 26 trades a tiny bit of GPU speed for dramatically better CPU and edge performance, plus NMS-free inference. It is the best YOLO for real-world deployment on diverse hardware.
Let us step back and see the full family tree. 2015, Redmon drafts YOLO V1. 2016, YOLO V2 adds anchors. 2018, YOLO V3 adds multi-scale. 2020, YOLO V4 bag of tricks, YOLO V5 PyTorch era. 2022, YOLO V6 industrial, YOLO V7 EGLAN. 2023, YOLO V8 anchor-free. 2024, YOLO V9 PGI, YOLO V10 NMS-free, YOLO 11 C2PSA. 2025, YOLO V12 attention-centric, YOLO V13 hypergraphs. 2026, YOLO 26 edge-optimized. Each generation solved a specific bottleneck.
Let us go deeper. In YOLO V1, each cell directly predicts X, Y, W, H, but raw predictions are unbounded and hard to learn. Starting with YOLO V2, predictions are offsets relative to grid cells and anchor boxes. The center offset uses a sigmoid so it stays between 0 and 1 within the cell. Width and height use an exponential so they are always positive. This reparameterization stabilizes learning enormously.
iView measures overlap between predicted and ground truth boxes, but it has blind spots. If two boxes do not overlap at all, iView is 0 regardless of how far apart they are. The gradient is 0 and learning stalls. Generalized iView (GIView) fixes this by penalizing the empty space in the smallest enclosing box. Distance iView (DIView) adds a penalty for the distance between box centers. Complete iView (CIView) adds an aspect ratio consistency term. Each successor fills a gap in the gradient landscape.
A YOLO loss function is typically a weighted sum of 3 terms: localization loss, classification loss, and objectness or confidence loss. In YOLO V1, it was all mean-squared error. Modern YOLO models use CIOU for localization, binary cross-entropy or focal loss for classification, and binary cross-entropy for objectness. Think of training a chef. Localization loss teaches where to place the food on the plate, classification loss teaches what dish it is, and objectness loss teaches whether there is food on the plate at all.
When an image has one dog and 50 grid cells, which cells are responsible for learning the dog? This is the label assignment problem. YOLO v1 used the grid cell whose center is closest to the object center. YOLO v2 used the anchor with the highest IVU. YOLO v8 introduced task-aligned assignment. It scores each anchor by a combination of its classification confidence and IVU with the ground truth, then picks the top K. This aligns the assignment with what the model actually needs to optimize.
Let us unpack the attention mechanism that powers YOLO v12. Each spatial position in the feature map produces three vectors: query, key, and value. The attention score between position I and position j is the dot product of query I and key j, divided by the square root of the dimension. After softmax, these scores weight the value vectors. The result is a weighted sum where each position gathers information from everywhere, a global receptive field in a single layer.
How do you compress a large, accurate YOLO model into a tiny one that runs on a phone? Knowledge distillation. The large model teacher produces soft probability distributions over classes and soft bounding box predictions. The small model student is trained to match these soft outputs, not just the hard ground truth labels. The soft outputs carry richer information. They tell the student not just that this is a cat, but that it is also somewhat similar to a dog and nothing like a car.
Even after distillation, a model stores weights as 32-bit floating point numbers. Quantization converts them to 8-bit integers or even 4-bit, reducing model size by 4-8 times and speeding up inference on hardware with INT8 support. Imagine translating a novel into a telegram. You lose some poetry, but the message arrives much faster. Post-training quantization does this without retraining. Quantization-aware training simulates low precision during training for minimal accuracy loss.
Pruning removes unimportant weights or entire channels from a trained model, like trimming dead branches from a tree, so the living branches get more sunlight. Structured pruning removes whole filters, reducing the actual computational graph. Unstructured pruning zeroes individual weights, requiring sparse hardware to benefit. After pruning, the model is fine-tuned to recover accuracy. Combined with quantization and distillation, pruning can shrink a YOLO model by 10 times with less than 1% accuracy loss.
Between the backbone and the detection head sits the neck, whose job is to fuse features from different scales. The Feature Pyramid Network, FPN, passes high-level semantic features top-down to low-level layers. PANet adds a bottom-up path as well, so small object details can inform large object features and vice versa. BiFPN adds learnable weights to each fusion connection, so the network decides how much each scale contributes. Think of a river delta. Water flows both downstream and through irrigation canals back upstream.
Mean average precision, or MAP, is the standard metric for object detection. For each class, you rank all predictions by confidence, then compute precision and recall at each threshold, forming a precision recall curve. The area under this curve is average precision, AP. MAP is the mean of AP across all classes. COCO uses MAP averaged over 10 IU thresholds from 0.5 to 0.95 in steps of 0.05, called MAP at 0, 50, 0, 95 or simply MAP 5095.
Training data is finite, but augmentation creates infinite variety. Mosaic augmentation, introduced in YOLO v4, stitches 4 training images into one, exposing the model to unusual contexts and scales. Cut-mix pastes a rectangle from one image onto another and mixes their labels proportionally. Mix-up blends 2 images and their labels with a transparency ratio. Copy-paste augmentation takes segmented objects and pastes them into new backgrounds. Each technique regularizes the model differently.
Training YOLO from scratch on COCO takes hundreds of GPU hours, but most real-world projects have much smaller datasets, maybe 500 images of defective circuit boards. Transfer learning solves this. Start with a COCO pre-trained YOLO model, freeze the backbone and fine-tune only the head on your small dataset. The backbone already knows edges, textures and shapes. The head just needs to learn your specific classes. It is like hiring an experienced chef and only teaching them your restaurant's menu.
Modern YOLO is not just a detector. YOLO v8 introduced a unified framework supporting 4 tasks from one architecture: detection bounding boxes, instant segmentation pixel masks via proto-mask branch, pose estimation keeping coordinates, and oriented bounding boxes, rotated rectangles for aerial imagery. YOLO 26 adds classification and open vocabulary segmentation via YOLO. One model, 5 tasks, a true Swiss Army knife.
You have trained your YOLO model in PyTorch. Now what? The deployment pipeline is PyTorch right arrow ONNX and open graph format, right arrow an inference engine optimized for your target hardware. TensorRT for NVIDIA GPUs fuses layers, quantizes to FP16 or INT8 and can achieve 2.5 times speedup. Core ML targets Apple devices. TF Lite targets Android and microcontrollers. OpenVINO targets Intel CPUs. Each engine applies hardware-specific optimizations like operator fusion, memory layout changes, and kernel auto-tuning.
YOLO detects objects frame by frame, but real applications need tracking, knowing that the person in frame 1 is the same person in frame 50. ByteTrack associates detections across frames using a simple but powerful idea. It tracks not only high-confidence detections, but also low-confidence ones, recovering occluded objects that other trackers would lose. BoTsort adds camera motion compensation and a re-identification feature vector. Ultralytics YOLO integrates both trackers out of the box.
Convolutions are local, efficient, and translation equivariant. They see a small window and apply the same filter everywhere. Attention is global, flexible, and content-dependent. It decides dynamically what to focus on. YOLO's history shows a gradual shift. V1, V11 are CNN dominant, V12 makes attention central, V13 goes further with hypergraph attention, yet YOLO 26 returns to a more balanced CNN design for edge efficiency. The lesson: there is no one winner. The best architecture depends on your hardware and accuracy target.
Standard convolutions and attention operate on fixed grids, but objects are not grid-shaped. A giraffe is tall and thin. A bus is wide. Deformable convolutions learn small offsets that shift the sampling positions, allowing the filter to adapt its shape to the content. Deformable attention does the same for attention. Each query attends to a learned set of offset positions rather than all positions. This content-adaptive sampling is a key ingredient in modern detectors like deformable DETR.
The latest frontier is integrating foundation model capabilities into YOLO. YOLO 26 accepts text prompts via clip embeddings, type hard hat, and it detects hard hats without ever training on them. This open vocabulary detection bridges the gap between closed-set YOLO, fixed class list, and open-world understanding. Other approaches use DINOV2 or SAM features as additional inputs to YOLO's backbone, enriching its representations with knowledge distilled from billion-parameter models.
Every modern YOLO uses batch normalization after nearly every convolution. BN normalizes each channel's activations to zero mean and unit variance across the mini-batch, then applies a learnable scale gamma and shift beta. This smooths the loss landscape, allows higher learning rates, and acts as a mild regularizer. During inference, BN uses running averages computed during training. In reparameterized models like YOLO v6, BN is mathematically folded into the convolution weights, eliminating it as a separate step.
SBP and its faster variant SBPF applies max pooling at multiple kernel sizes, say 5x5, 9x9, 13x13, to the same feature map and concatenates the results. This lets the model capture context at different spatial extents simultaneously. Imagine standing in a room and looking through 3 windows of different sizes. The small window shows nearby detail, the medium window shows the room layout, and the large window shows the whole building. SBP gives the model all 3 views at once.
CSPNet splits the input feature map into 2 halves. One half passes through the main dense block, heavy computation. The other half bypasses it entirely. The 2 halves are concatenated at the end. This reduces computation by roughly half while maintaining rich gradients because the bypass path provides a direct gradient highway. YOLO v4 used CSP Darknet 53. YOLO v5 refined it with C3 blocks, and YOLO 11 introduced C3K2 with flexible kernel sizes.
YOLO v6 uses RepVGG-style reparameterization. During training, each block has 3 parallel branches, a 3x3 convolution, a 1x1 convolution, and an identity shortcut. This multi-branch structure improves gradient flow and accuracy. At inference, these 3 branches are mathematically merged into a single 3x3 convolution, no extra cost. Imagine an actor who rehearses with 3 coaches for depth, but performs solo on stage for speed.
How do you scale a model from nano to X large? YOLO v7 adopts compound scaling from EfficientNet. Instead of just adding more layers, depth scaling, or more channels, width scaling, you scale depth, width, and resolution together with fixed ratios. This ensures that as the model grows, it remains balanced. A model that is very deep but very narrow would be inefficient. Think of inflating a balloon evenly rather than stretching it in one direction.
In YOLO v1, v5, one shared set of convolutions predicts both class probabilities and bounding box coordinates. YOLO v8 splits this into 2 parallel branches, one for classification, one for localization. This is called a decoupled head. Why does it help? Because the features that help classify an object, texture, color, fine-grained patterns, are different from those that help localize it, edges, boundaries, spatial extent. Forcing one set of features to do both is like asking a single employee to handle sales and accounting simultaneously.
YOLO V10 pioneered NMS-free inference by using dual label assignment during training. A one-to-many head assigns multiple predictions per ground truth object for rich gradients, and a one-to-one head assigns exactly one prediction per object for clean NMS-free output. During inference, only the one-to-one head is used. YOLO 26 inherits and refines this. The analogy: during rehearsal, the whole orchestra practices each passage. During the concert, only the first chair plays the solo.
Deep networks suffer from information bottleneck. As data passes through many layers, some information is irreversibly lost. YOLO V9 introduces programmable gradient information, PGI, an auxiliary reversible branch that runs alongside the main backbone. During training, this branch provides an alternative gradient path that preserves the original information, ensuring that even deep layers receive rich supervisory signals. At inference, the auxiliary branch is removed. It is like having a study guide during the exam that you discard after answering.
The anchor debate is one of YOLO's most important transitions. Anchors, predefined box templates, were introduced in YOLO V2 and refined through V7. They help the model by reducing the search space. Instead of predicting arbitrary boxes, you predict offsets from a nearby template. But anchors require careful design, k-means clustering on training data, add complexity, and can bias the model toward the training distribution's aspect ratios. Anchor-free methods, YOLO V8 onward, predict 4 distances from each cell center, left, top, right, bottom, directly. This is simpler, more general, and works well with modern training techniques.
Each YOLO version uses a different backbone. YOLO V1, V2 use custom darknet architectures with alternating convolutions and max pooling. YOLO V3 introduced darknet 53 with 53 convolutional layers and residual connections. YOLO V4 upgraded to CSP darknet 53. YOLO V5 continued CSP darknet with C3 modules. YOLO V8 used a refined C2F backbone. YOLO V12 used ILAN with attention. YOLO V13 used HyperAce. YOLO 26 returns to an efficient CNN backbone. The backbone is the feature extraction engine. Choosing the right one is like choosing the right engine for your car.
The learning rate controls how big a step the optimizer takes. Too large and the model oscillates. Too small and it converges slowly. Modern YOLO training uses a warm-up period. The first few epochs use a very small learning rate that gradually increases, followed by a cosine decay that smoothly reduces the rate to near zero. This is like a runner who jogs slowly to warm up, hits full sprint in the middle, and gradually decelerates to cool down.
YOLO V5 introduced a 2-phase augmentation strategy. During most of training, mosaic and other heavy augmentations are applied. In the final 10 epochs, mosaic is turned off and the model trains on single images with lighter augmentations. This close-up phase lets the model refine its predictions on clean data after learning robust features from augmented data. It is like an art student who first paints with wild abstract strokes, then in the final days before the exhibition, refines the details with a fine brush.
Or does YOLO actually run in the real world? NVIDIA Jetson Nano and Orin are popular embedded GPUs for robotics and drones. Modern smartphones have neural processing units, NPUs, dedicated chips for ML inference, that can run YOLO at 30 FPS on device. Even microcontrollers like the ESP32S3 can run tiny YOLO variants, MCU net style, at a few FPS for IoT applications. YOLO 26 was explicitly designed for this edge spectrum, with its CPU-optimized backbone and NMS-free inference, reducing both latency and power consumption.
Standard bounding boxes are axis-aligned rectangles, but in aerial and satellite imagery, objects like ships, aircraft, and vehicles are rotated at arbitrary angles. An axis-aligned box wastes area and overlaps with neighbors. Oriented bounding boxes, OBB, add a rotation angle theta to the standard x, y, w, h parameters, producing a tight rotated rectangle. YOLO V8 and YOLO 26 support OBB natively, using angle regression and specialized I-view calculations for rotated boxes.
YOLO pose predicts bounding boxes and keypoints simultaneously. For human pose, 17 keypoints nose, eyes, ears, shoulders, elbows, wrists, hips, knees, ankles are predicted as X, Y visibility triplets per detection. The model learns these alongside class and box predictions using an additional regression head. Object keypoint similarity, OKS, is the evaluation metric, analogous to IOU but for keypoints. YOLO 26 pose achieves real-time multi-person pose estimation at over 100 FPS.
YOLO's segmentation branch uses a YOLACT-inspired approach. The model predicts a set of prototype masks, global basis masks, and for each detection, a vector of mask coefficients. The final mask for each instance is a linear combination of prototypes weighted by the coefficients, then cropped to the bounding box. This is much faster than per-pixel mask prediction because the prototypes are computed once and shared across all instances.
YOLO extends YOLO 26 into open vocabulary territory. It operates in 3 modes. Text-prompted user provides class names, clip encodes them. Visual-prompted user provides reference images. And prompt-free uses a built-in 4585 class vocabulary from LVIS. Under the hood, the detection head computes a dot product between the visual feature and the language embedding, replacing the fixed classification layer. This makes YOLO a bridge between closed-set YOLO and open-world perception.
Training YOLO 26X on Coco takes about 36 hours on a single A100 GPU. For faster iteration, Ultralytics supports multi-GPU training via PyTorch's Distributed Data Parallel, DDP. Each GPU processes a portion of the batch, gradients are synchronized across GPUs, and the model updates in lockstep. With 8 A100s, training time drops to under 5 hours. Cloud platforms like ORS, GCP, and Lambda Labs make this accessible without buying hardware.
How do you find the best learning rate, augmentation strength, and loss weights? Trial and error is slow. YOLO V5 introduced hyperparameter evolution. It runs many training experiments with randomly mutated hyperparameters, like genetic evolution, and selects the best performing settings. Each generation slightly mutates the top performers and retrains. After 300 generations, the evolved hyperparameters often outperform hand-tuned defaults by 1–2% MAP.
The dataset you pre-train on shapes what the model knows. COCO has 80 classes and 118K training images, a solid general-purpose benchmark. Objects 365 has 365 classes and 2 million images, providing much broader coverage. Open Images has 600 classes and 9 million images. Pre-training on larger datasets, then fine-tuning on COCO consistently boosts performance. YOLO 11 and YOLO 26 offer models pre-trained on objects 365 for transfer to specialized domains.
Small objects under 32 times 32 pixels in COCO definition remain the hardest category for all detectors. They occupy few pixels, get downsampled quickly through the backbone, and are easily confused with noise. Solutions include higher resolution inputs, e.g., 1280 instead of 640, additional detection heads for small scales, SAHI, slicing-aided hyperinference, which tiles the image into overlapping patches and runs inference on each, and YOLO 26's SDAL label assignment, which biases training towards small targets.
YOLO is a powerful tool, and with power comes responsibility. Object detection can be used for surveillance, profiling, and invasion of privacy. Autonomous driving detectors must handle failure cases. A missed pedestrian detection can be fatal. Bias in training data, e.g., underrepresentation of certain demographics, leads to bias detectors. Responsible use requires transparent reporting of failure modes, diverse and representative datasets, human oversight in safety-critical applications, and compliance with privacy regulations like GDPR.
YOLO is everywhere. In agriculture, it counts and classifies fruits on trees for yield estimation. In healthcare, it detects polyps in colonoscopy videos in real time. In retail, it monitors shelf stock levels. In wildlife conservation, it identifies endangered species from camera traps. In manufacturing, it spots defects on production lines at 60 FPS. In sports, it tracks players and ball positions for analytics. Each domain fine-tunes a YOLO model on domain-specific data, often starting from a COCO pre-trained checkpoint.
Here is a practical recipe. Step 1. Collect and annotate data. Use RoboFlow, CVAT, or Label Studio. Step 2. Export in YOLO format 1 TXT file per image with class and normalized coordinates. Step 3. Create a data YAML file pointing to train/val paths and class names. Step 4. Pick a model size based on your hardware, YOLO 26N for Edge, YOLO 26L for GPU. Step 5. Train with model train data equals data YAML epochs equals 100. Step 6. Evaluate with model val. Step 7. Export with model export format equals oncs. Step 8. Deploy.
The trajectory is clear. Detection models will become increasingly multimodal, understanding text, images, and video simultaneously. Real-time 3D object detection from LiDAR camera fusion will be embedded into YOLO-like architectures. On-device training, not just inference, will allow models to adapt in the field. Neural architecture search will automate the design of task-specific YOLO variants. And the boundary between detection and foundation models will blur. Every future YOLO may be an open vocabulary, multitask, multimodal agent that perceives the world as fluidly as we do.
Joseph Redmon's original insight was radical simplicity. One network, one pass, real-time speed. That philosophy persists across every generation. A beginner can install Ultralytics, run 3 lines of Python, and detect objects in minutes. A researcher can spend years exploring attention mechanisms, loss functions, and deployment optimizations. YOLO democratized computer vision. It took a task that once required PhD expertise and million-dollar hardware and made it accessible to a student with a laptop and a webcam.
You have traveled from a 10-year-old's wonder at human vision to the cutting edge of hypergraph-enhanced detection and open vocabulary segmentation. You understand pixels, neurons, convolutions, attention, anchors, losses, necks, heads, NMS, quantization, and deployment. The only thing left is to build. Pick a problem you care about: counting bees, detecting potholes, monitoring coral reefs, reading sign language. Install Ultralytics. Annotate 100 images. Train a YOLO 26 model, export it to your device, watch it work, then go deeper. The journey from zero to hero is not a destination, it is a loop. You only look once, but you learn forever.